Yeah.
So welcome everyone. Welcome back for the final session of the second day of the Higginson conference. I'll give the word to Alex Altran that will chair this session. Please.
Yeah, nothing much to say. Our next speaker is Sharon Shi, whose talk will undoubtedly win the award for the most beautiful title. And he encourages questions during the talk. So if you have a question, send a signal and deal with it. Okay, go ahead, Sharon.
Thanks, Alex. And thanks, first, I would like to thank the organizers for inviting me to this interesting conference. This is a work in quantum gravity, which is about something we call entanglement island, entanglement islands and miracle operators and the firewall. I will explain what it means. I will start with an overview of the black hole information paradox, and then discuss some recent progress. This is the background. This is the recent progress that's partially solved some of the black hole information paradox, which involves the concepts of entanglement island and replica wormhole. And after this overview, I will discuss how this gives us new insights about how to get information from the black hole interior, and then there is some contradiction when we try to apply this way of retrieving information, and then we will learn from that there are different kind of operators, and there are ordinary operators like measuring spin SZ, or there is miracle operators. What I call them miracle operators because they will, when you apply these operators, they change your space-time geometry. So that's what I mean by that term, and this is in this recent arXiv preprint. Please, feel free to stop me anytime, especially because I know this is not a quantum gravity audience. I'll be happy to explain if anything is not clear. So we know like the black hole information paradox comes when we think about evaporating black hole. According to the Hawking radiation, we know that the black hole will be like, if you look at the picture on the right side, I'm drawing like a matter falling in, collapse into a singularity, and then you have this orange, this yellow thing, which is a horizon, and then the light in the horizon will go in rather than going to infinity. So as a consequence, you have these virtual pairs that one of them will disappear at the singularity, and therefore physically you only get the outmover. So as a consequence, these outgoing Hawking radiations will lead to a decrease of black hole's energy, and eventually the black hole will evaporate. So the figure on the left side is just the same figure, but drawn in the Penrose diagram, so that all the light rays looks like 45 degrees. So then there is the reason why there's all these information paradox. There's different forms of information paradox because there is some conflict between the unitarity of quantum mechanics and this black hole thermodynamics. So if we believe in unitarity of quantum mechanics, and if we believe that applies to black hole, then the Hawking radiations should be related to the infalling matter by a unitary. If the infalling matter is a pure state, the outgoing states will also be pure. But the Hawking calculation shows that the Hawking radiations are thermal. So that means they have an entropy that's increasing with time, and it will be a conflict with the unitarity. And so that's what I call the old paradox. It means that just directly, like if we sit outside the black hole, there is a calculation of Hawking which says the entropy of these radiations are thermal, so it just keeps increasing. And then quantum mechanics says the entropy should, in the end, return to zero if I have pure state matter. And there is a newer form of the paradox, which is, I think, it's different from the other one because it involves the question of what happens if I jump in the black hole. So if someone jumps in the black hole could be very big. In that case, you don't feel the gravity is very strong at the horizon. So you could be feeling totally fine when you cross the horizon. And then you expect, like according to general relativity, you expect to see a totally smooth horizon. Nothing is special there. But then there is a contradiction that that means you could see this infalling partner of B. There's an outgoing photon B and infalling B tilt, and they are EPR pairs. So that means if you could see both of them, then the question is how could you have B also entangled with the earlier radiation A? But that's required because if you want the entropy to eventually go back to 0, then the late radiation B and the early radiation A must be entangled. So there is a problem because the qubit B cannot be entangled with both B tilt and A. So that's known as the firewall paradox. Yeah. So to address these questions, so I mean there's many different attempts, but the recent breakthrough is in 2019. There are these two papers where they point out that actually if you don't need to like build a totally new theory of gravity or anything like that. If you just carefully do the Hawking calculation, but do it in the right way, you do the gravitational calculation in the right way, then you actually can get the correct entropy. I mean, there's an oversimplified version of the story, but basically, we are still doing things like Hawking, which means you're studying gravity coupled to quantum field theory, and then the only thing different from standard quantum field theory is you allow the geometry to change. Right? So in gravity theory, you allow your geometry to adjust itself. And as long as you carefully think about that, like Rayleigh entropy calculation and allow the geometry to change, then there turns out to be an important topological change, which is called the replica wormhole. And that gives you this correct entropy that grows and decreases in the end, go back to 0. I will go to a little more details about that because that's the basis of this work. But basically, we're trying to use that framework and then see that there is actually some very general reasoning that tells you how this replica wormhole geometry where it's applicable, and there's some contradictions if we assume it applies to all setups. Basically, let's say the system we consider is an ADS black hole coupled with a flat space thermal bath. So ADS black hole, if you don't couple it to a bath, then this is a black hole in the under the theta space, and it's like living in a box. It's not evaporating. Like but now you can artificially take another flat space and then couple with it. So it's like it's similar to like how you take a quantum dot, couple it to a line, and then the line plays the role of an infinite bath. So you can think that there is this quantum dot which is due to this ADS black hole. And then so if we assume there is this gravitational description, this holographic description of this ADS black hole, then when you compute an entropy, we want to compute an entropy of a region in the bath. So this is basically a generalization of this discussion about the entanglement entropy in holography, like Ryutaka and Nagi. It's a generalization because you are studying entropy in the region in the bath. And if there is no gravity, like if I'm talking about just curved space quantum field theory, what will you do if you want to calculate entropy? You will take multiple replicas of the theory, and then like what I draw here, let's say here is n equal to 3. I draw three replicas, and then you have this state. You have the state of your quantum field theory defined on a Cauchy slice like this. And then now if you trace over everywhere else, you just you'll keep your A region, and then you take 3 copies and glue them. So you have this branch cut that you glue all the 3 copies. Like the first one, when you go here in the first replica, you go out in the second, and then you go out in the third. Right? So that's how we calculate entropy, for example, in CFT. And then here, the only difference in gravity case is you should do a path integral, and you are integrating over the geometry of this part. The flat space part is fixed, and the ADS part is dynamical. So you're not fixing it. You should be integrating over all geometry. And then the key assumption is if the gravity is weak, then we assume that the path integral of this ADS part is dominant by a saddle point, right? So that's pretty reasonable. Like, so that's basically saying the Einstein-Hilbert action has a coefficient, which is our G Newton, you assume that's big, and you take a saddle point. So, but it's still different from quantum field theory because the saddle point itself could depend on this number of replicas. You could change the number of replicas, or you could change the region A, and these will change what's the saddle point. And that's the key. That's what the Hawking's calculation didn't include. The Hawking's calculation was like focusing on this each photon that goes out, it looks thermal. But this entropy calculation is like I take all these things together and calculate their entropy, and then you see that there is this possibility that what dominant the entropy calculation could be a different geometry, could be a qualitatively different geometry. So this picture here I'm drawing is like a Euclidean version of that. Like if you do a path integral and integrate everything else except the red part where I cut it open, that's a density matrix. And then this picture says you glue the two density matrices, okay, you get the picture on the right side. And the yellow region is like the black hole. So this is the ordinary situation. And then the new situation that's possible, pointed out in this two papers in 2019, is you could have a topologically different solution where there is a wormhole connecting the two interiors of the black hole. And so what you should do is you should look at the different possibilities, like this saddle point and this saddle point, and then compare their contribution. And then when the second one is dominant, that's when you have a entanglement island and a replica wormhole. And this solution, basically, once you fix this geometry, it also looks like the same kind of replica geometry you have in entropy calculations. But it looks like you're calculating entropy of a different region. It looks like you're calculating entropy of, in addition to the original region, there is a new region included in the entropy calculation. So it's like a QFT calculation where you're calculating entropy of A and I together. And then there is also an area law contribution coming from the Einstein term. So this is the formula when you take analytic continuation back to n equals to 1, back to the von Neumann entropy, then you get this quantum extremal surface formula, which says that the region, in the quantum gravity theory, the left side is like an entropy of the actual state, like the quantum gravity state. And that, where is it? Where is my, oh, here. The left side is defined in quantum gravity, and the right side is defined in a quantum field theory in curved space. So it means that the correct entropy is actually looks like a quantum field theory entropy of a bigger region of A and I, and then plus an area law term. And so this is an important, a key part in the setup that I want to emphasize is this two different systems. Like we always think of there is this two kind of Hilbert space. There is the quantum gravity Hilbert space, which means the entire gravitational system together with the entire path. So for example, if I think about an example toy model of the SYK model, then I can think that this is like the entire SYK site coupled with let's say free fermion chain as a path. So that's like the physical well-defined UV complete Hilbert space. And then there is the other Hilbert space, which is like the effective quantum field theory description of the bulk together with the quantum field theory in the path. That's what I call the HQFT. So the analog, this is like the quantum field theory Hilbert space is like the analog of the bulk in the ADS-CFT, and then the quantum gravity is like the boundary. And so it's like a smaller one. So this one is smaller, and then you embed it into the bigger one. And only in that smaller subspace, it makes sense to talk about bulk geometry. And you can write down those quantities on the right side, like the entropy of a given region plus an area law. Any questions? Okay. Yeah. So now, okay, so far this is the overview, and then this is like a one step away from it's like a very simple generalization of what we discussed, and that's when I'm trying to discuss how you reconstruct the information from the interior. So if you do this calculation and it tells you that that you get this non-trivial quantum extremal surface, it means that on the right side, like the island will appear, this entanglement island I will appear if this is smaller than the trivial solution. Trivial one corresponds to no I, right? So there is always a trivial solution, which is just the QFT entropy of rho A. Like I use the bold font to represent the quantum field theory states, and the ordinary, the regular letters to represent the quantum gravity states. So you need this entanglement island to satisfy that the entropy is smaller. The entropy plus area law is smaller than the entropy of rho A itself. And when that's satisfied, then you get a solution with an island. And we can use the same solution for a different purpose. We can ask, okay, so how do I? So like the entropy formula indicates, like implies that that the region A knows something about what happens in the interior, because if you calculate the entropy of A, you are calculating entropy of A together with I. So if I, for example, if I create an EPR pair, then this red line here, this B tilde, has an entropy, let's say log 2, then that will show up in your entropy of AI. So that implies that that the degree freedom B tilde is actually in A, so it contributes to A's entropy. But there is a more direct way to see that, which is through this norm between density of states. So if I take two density states, density operators. If I take two density operators that are quite similar, then like the geometry is all the same, and the only difference is like I have this internal unitary that flips the spin from up to down. So let's say I have this this photon with a polarization, and then the only difference between the two states is one photon in the interior has a left hand and the other has right hand. So it's spin up and down. Then for two such states, I can calculate things like the trace of rho to some power times sigma to some power. I can calculate this kind of thing in the same way as the path integral will show up before, because for the gravity calculation, these two states has almost the same energy, so it's dominated by the same saddle point. So if there is an island for the calculation of trace rho to the n, then there should also be the same island for this cross overlap term. So that means that I could calculate the norm difference. I could take rho and sigma and calculate their norm difference, and the norm difference will can be calculated in the same saddle point approximation. And if I take n back to 1, then the gravitational area law part goes back to 0, and you'll get this equation here, which says that if I believe in this analytic continuation, then we conclude that the one norm difference of two states, rho and sigma, which are only different slightly, the one norm difference in the quantum gravity system, the left side is in the quantum gravity system, that's equal to the same one norm difference in the quantum field theory for a bigger region AI, which means if I contains the spin that's up and down, they are different, then there is a non-trivial one norm difference on the right side. And so this equation, this is a key basis of our discussion. This equation tells us that that when you have a region A which has an entanglement island, then region A knows about any small perturbation in the island, because if you have a spin flip or any such kind of small perturbation which contributes to the one norm difference, then the one norm difference will appear in the states in the outside region A. So like you didn't lose anything you didn't miss any information in the small, as long as it's small chain. And okay, so that all looks very reasonable. But then the key point of this work is to say that we are going to show that this calculation here, which seems to be very general, is just assuming there is a saddle point dominating gravitational calculation. But in addition, it's assuming the saddle point is preserving the replica symmetry. But these are still very general assumptions. But the key thing is that we are showing that this cannot always apply. Like there are these operators we call miracle operators. Like when you apply these, then you cannot continue using this assumption. And so to see that, let's first mention one fact that when you have a one norm distance between two states that are a certain value, then the one norm distance measures the how you can distinguish the two states with the optimal measurement. It means like you do one projective measurement to the state rho and state sigma, and then ask how big is the difference in terms of expectation value of that operator. And if you optimize the projector you choose, then the best projector, which is the PA I wrote here, PA, the best projector will give you the expectation value difference that's equal to half of the one norm difference. So that tells me that the one norm difference measures the how you can best distinguish the two states with an optimal measurement. And the measurement itself is really just diagonalizing rho minus sigma and take the positive eigenvalue. The PA is really just projecting on positive eigenvalues of rho minus sigma. Yeah, so later we're going to use that. And then, so the one thing to point out is that this island formula, as I mentioned, if you want to have an non-trivial entanglement island, it must have a smaller entropy than the one without island. So as a consequence, you have to have a negative conditional entropy. Means like even if you ignore the area law term, SAI must be smaller than SA. So like there must be a lot of entanglement in I and A. Otherwise, you will never have an island. So one particular example. So this leads to a consequence. This observation that you need a negative conditional entropy leads to the observation that any region that's only classically correlated with the rest of the system will never have an island. Right, so imagine I have a setup like this. I have a black hole and a radiation, and I have some other equipment in my lab, and I'm using that to do some measurements to my.
There's a question from the audience regarding understanding. I can read it. I mean, in which Hilbert spaces are your rho and sigma defined? You were.
So where here? The rho and sigma on the left side is defined in the quantum gravity Hilbert space, and on the right side, the both rho and sigma, they are in the quantum field theory Hilbert space. So yeah, so this equation is it's similar to bulk boundary correspondence in ADS-CFT. So it's like correspondence between two Hilbert spaces, and the right side is in the bulk, the left side is like the boundary. But here, the difference is that the left side is like boundary plus bus. The right side is bulk plus bus.
Right, great. Thank you. And as we are on it, 5+ minutes, 5+ epsilon. Okay.
Yeah, I will need to quickly wrap up. Yeah, so so the key thing, okay, the key message here is that if you consider, so the discussion so far seems pretty general, like it didn't talk about what is the dynamics of the bus. So naively, I could apply it to a case where the bus contains two parts. That's the R1 and W. I can consider like I have my black hole here in my lab, and then instead of just couple it to a flat space quantum field theory bus, I can introduce another equipment that's doing measurement to the bus. Right? That's what I want. Because I want to do measurement and distinguish different states. So that's the W. So I can have a W and couples with my bus, and then but the point is that if I include W as part of my system, which I'm allowed to do, right? I can have this entire system, including my lab, that's evolving unitarily. So there's no reason to not do that, not allowed to do that. So then I can take a region of W, which is like the part where I record my measurement results and so on. So everything's so W is only coupled with the bus, with the radiation classically, then the state of W will never have a negative conditional entropy because the classical states never have a conditional entropy that's negative. So the conclusion is that W will never have an island. Okay, so far, I mean, we can think of a more specific setup. This is just the same picture, but I'm drawing a more specific case, which is like I have this region A, and then I want to do a measurement on A. I mean, in particular, we want to do that optimal measurement. So I want to do that measurement on A. So, but instead of just saying, okay, I insert that projection operator, I can do it in a physical way, which means I can introduce an ancilla. That ancilla is coupled to A in a unitary UM. And then now if I trace over part of that ancilla, the remaining quantum channel is I apply projector on A. And if I project to the PA equals to 1 space, my W will have a state 1. If I project to PA equal to 0, my W will have state 0. So it's really the standard way that you introduce an ancilla and you do a measurement. So you do a measurement on A and record the results on W. But when you do that, then there is a conflict because like on one hand, the entire evolution here is unitary. So I should be able to apply this path integral of gravity calculation here because I mean that's the only thing I'm changing is the bath part. The black hole part is still the ADS space, and if I take n copies of this system, and I could ask, okay, I could calculate the entropy of A, or I could calculate Rayleigh entropy of A. I could also calculate Rayleigh entropy of W after the measurement. But then, because W never have an island, because it's correlated with anywhere else, only classically, it doesn't have the negative conditional entropy. So the conclusion is that W has no island, and therefore it has no way to know a unitary applied to the interior. And so because the equation tells me that if W has no island, then the state, the one norm difference between the two states, which correspond the two states rho and sigma, which are different by interior spin fluid. Then when you have no island, then you can calculate then you will get something like this, right? You get rho W minus sigma W. That's equals to the same quantity in Q of T, which I wrote in both front, but I could, something like that. So this is, the right side is in Q of T. So, but in Q of T, this UP is space like separate from U. So when you apply that, it's not going to change the state. So you conclude that this, from this island calculation, it will tell you that the internal spin flip is not known by W. But on the other hand, that's not possible because you can just, I mean, A knows about the interior spin flip. Like rho A minus sigma A is non-zero before you even do the measurement. Right? Rho A minus sigma A is non-zero according to that island calculation because it has an island. So we have shown that rho A minus sigma A is equal to the rho of AI in Q of T. Rho of AI in Q of T, and that's non-zero. But if that's non-zero, then there is a measurement on A which could learn. We can do a measurement and learn about it, and then send that message to W. But then W will know about that measurement. So if you do a calculation, you can easily show that the direct setup, if you are doing that optimal measurement, it leads to the one norm difference of the W state. Which is exactly the same as the one norm difference of the A state before the measurement. So basically, through a measurement of the optimal operator, you could transfer any one norm difference to the state W, even if there is no quantum entanglement at all between W and anything else. So there is this conflict that because there is no quantum entanglement, there is no island. Naively, I got the conclusion that the interior unitary is not visible from W. But this direct setup tells me it's visible. So so that's where now we go back, we say, okay, where is the problem? So if you go back, you see like the only assumption we made is the gravitational path integral is dominant by a saddle point, and the saddle point is replica is permutation symmetric, not permutation, cyclic permutation symmetric. And that's it, right? So we assume there is a smooth geometry. So there must be something wrong in these assumptions when we do the setup with W. And so the that's where we say so what happened is that is that when you introduce an optimal measurement like PA, actually that measurement is so special. That's why I call them miracle operators, because it looks pretty counterintuitive that I'm just doing a measurement PA, and that PA only takes 1 bit of information. It's just PA has only 2 eigenvalues, plus minus 0 or 1. So W is size dimension 2, and so I'm just taking 1 bit of information out. But if you are asking the right question, then that's actually changing what saddle point you have in your gravitational path integral, and not only changing one saddle point to another. It's telling you that it cannot be, like, it tells you that you cannot have a path integral that's dominant by any smooth geometry, because any smooth geometry will give you back the same general formulas here, which will have a contradiction. So we can actually see explicitly what's actually happening by doing a replica construction of the operator itself, because we know the optimal operator looks like this. Like I skipped that earlier. So the optimal measurement is done by diagonalizing rho minus sigma, and then define this equation here. You can take rho and sigma and just sum over the positive eigenvalues and minus the negative eigenvalues. But then there is a replica way to do this. You can define rho minus sigma to an odd power, and then take that odd power to 0. When you do that, then you get this the same state. You get this ZA. And PA and ZA are just given by a shift of numbers. So yeah, but when you think it this way, then it's not so surprising, because if you introduce this operator and you say, let's call that, instead of calling these states, you call that an operator. And I call that operator ZAN. So if you take that operator and measure that in rho A, then you know, okay, of course something goes wrong, because this is the same as like calculating a Rényi 2n entropy. So there will be wormhole connecting rho A with things here. You will have like internal wormholes, like wormholes in the black hole interior connecting these different copies of rho A. And that's what happens here. That it's like this picture. It's like if I calculate, if I do that setup with a bus W and then calculate entropy of W, what you get is like expectation value of this operator PA with multiple copies. And then the previous this discussion we had has a contradiction, and that's because we are assuming the only thing possible is there's a wormhole connecting these different replicas when you calculate the Rényi entropy. But actually, what happened here in this example is there's wormhole connecting your system and the operator you measure, which is, I mean, I should point out that this is not like the first time we know this. In the paper in 2019 about replica wormhole by Steve Shankar, Douglas Stanford et al. There is a discussion about path map, right, which is one way you reconstruct operators from boundary. And there you already see the same kind of thing, like the operator reconstruction itself comes with the geometry, and then you have wormholes connecting the actual physical system on the left side, and the geometry you introduced by introducing these operators. But I think that this discussion here is showing that because of the very general reasoning, then any operator that learns anything non-trivial about the interior is this type. This is what we call miracle operators. And so I think I will skip the later part about firewall, but basically this explicit construction allowed us to learn a bit more about how to extract information from the interior. Because here I'm asking a simple question, like instead of asking me to reconstruct all the operators from interiors in some subspace, I'm just telling you like, okay, the state is either rho or sigma, and can you find out whether it's rho or sigma? So if you ask that binary question, then you can use this particular operator to probe that, and that makes some of the discussions about retrieving information from interior more concrete. Okay, I will stop here. Thank you.
All right, thanks a lot. We have time for a few questions. Just ask. I mean, Anybody has a question?
I didn't understand at the end. Are you getting something at the horizon scale or not? Are you getting some firewall or some fastball or not from this construction?
One thing about one thing that's in the later part is using this construction, we can test more explicitly what happened to the firewall paradox. You could create a EPR pair across the horizon, the BTOs, and then I could use this particular operator to measure the spin of BTOs and ask if that destroyed the entanglement between B and BTOs. And then this the answer is yes, which somehow means you create a firewall, but it's not a very strong firewall because it's because the whole discussion only applies if you try to reconstruct a small part of the interior cyberspace. Like you have to do small perturbations so that the back reaction is not so big. So it's like there's a few photon pairs, and I could do some measurement entirely in the exterior to destroy them. But this is not saying like I could do something in the exterior and completely break the entanglement between interior and exterior.
Okay. Okay. Thanks.
Thanks.
Two related questions. So are your miracle operators, do they depend on the state of the black hole? And
yes.
If yes, yeah. What is the relation? So there are these mirror operators that were discussed starting about 10 years ago in the context of large ADS black holes. So these are state-dependent operators that precisely describe excitations in the interior. What's the relation between your miracle operators and these mirror operators?
Yeah, I think very good question. So I think that the observation is all different kind of operators that try to probe things from the interior. They all share this property that they are state dependent. And it seems like the state dependence is essential, is the reason why when you do these replica calculations, it involves wormholes connecting the system with the operator. I mean, that's the strange thing that I would have thought, like in this case we were talking about here, the operator could be just a result of a classical computation. In principle, I could have a big enough classical computer. I simulate my black hole system, and I learn, oh, okay, so the black hole state should be this. So then I know what operator I need to measure. So you don't need another quantum system at all. But still, even then, when you tell your quantum, when you go to measure that operator, then the dominant geometry is some geometry that connects the physically existing system with some simulated system. So that's a weird thing. And I think that if you do this for the mirror operator, the same thing will happen, because as long as your construction involves the density operator of the system itself, something like this will occur. The same thing happened in the past map reconstruction.
May I ask a question?
Yeah.
If you have an access to the region A, asymptotic region A, in principle, can you reconstruct the whole interior of the black hole, or only the quantum state of the region I?
If you have access to A, then it's only the region I. And not only that, it's only small perturbations in region I.
But what about the rest of the black hole? Can you access that information from the asymptotic region?
I think that you cannot do it now. You can do it later. So like if you're evolving A, and then A goes here, then the corresponding island is evolving something like this. So the part you cover is more and more. And in the end, if the black hole totally evaporates, it should be everything.
Is there any understanding why the information in the black hole structures itself in a geometric way, such that you can access part of it, which is geometrically well defined?
Yeah, that's a very good question. That's exactly that's why it. I certainly don't know the answer, and I think that's the what's happening. Sorry. It's an open question, and I think it's similar. Like we can ask a simpler question in ADS-CFT, where like we have a boundary region A, and this bulk is ADS. And then we say, okay, why is there this complementary recovery? Like there is this sharp ADS, there is this ADS, the Ricciardi supersurface, and then things here can be recovered from A and things here cannot. So it's similar to that, but it's more complicated because I don't have a quantum. I mean, I have this island and it's not attached to the boundary, but it's similar. It's really this shaded region here is the entanglement wedge of A, in the same way as this boundary region A has the entanglement wedge here. Yeah, so that's I think that's really the special thing, and we don't know if like we don't know how general that is. Like it, I mean, it's possible that most chaotic quantum field theories don't have this property. Like it may only have locality in the bulk up to the size of ADS radius. Whether you have this more locality, like until all the way to Planck scale, is that something? It's possible that this is something very special for these super young mirrors, but I don't know. Like even for like the SYK model, it has a lot of features about it has a lot of features of holography, but but the bulk theory, does it really have locality in the scale below ADS? That's already an interesting question, I think.
All right. Unless there are super urgent questions, I suggest that we thank Xiaolang again for the interesting talk and move on.
Thank you.